Hello everybody, this is Des Warby again from Rarefied Technology Southeast Asia, or RareTechSEA. We're going to continue now with part 3 of the Modular Shell-and-Tube Heat-Exchanger presentation. So last time we ended up talking about the concept of modular construction. So you take these single modules and you configure them. And we have a few ways to configure. This particular one here is all in series. So you have that module linking into this module, linking into this module, which represents a very, very long heat exchanger. You know, if these are say 3 meters long, it's a 9 meter long exchanger. It's a long thing. So you can wrap it and put it together. The beauty also about these modular units is that, for instance, if your duty changes or you want to get more heat or do something, you can easily add another bank on, another module on top here. And then at the end you put turnarounds and then you make the entrance exits over here. So you have a fourth module on top. If you decide that you want to slow things down but or whatever, make them smaller, you can take a module off and then just use the components but stick them on this end. So it's very, very flexible in how to build some very complicated arrangements out of standard parts. Alright, it's not difficult at all. And so it extends the longevity or the life of your units, because you now don't have to go and buy too many parts. You can actually rebuild out of parts that you have. You might get a few bits and pieces from the manufacturer and they can then put it all together. Alright, so let's move to the next page, if it decides to do what it's supposed to do. There. So here we talk about the U3s. We had spoken earlier on about U5s and U3s. The U5s are the standard ones that we work with, but the U3s were developed mainly for oil cooler applications, meant to be a lower cost type unit. So the idea was for gearbox oil cooling, water heaters and coolers, for instance, steam water heaters. And the idea was that you could actually select them off a chart. So you'd have a unit like this and you'd have standard sizes. U3 00, 0, 1, 2, 3 and so on, and they'd give you the dimensions here, and then they'd actually look at its performance. So you'd have one for oil and one for water and one for steam, and this is an example of the type of thing that you can have. And actually they actually were quite nice, actually not a bad idea. The shell side baffle was a little bit different because of the size constraint. It wasn't it was spiral but made in 3 parts, not in 6 parts. But they worked quite well, and they were actually quite a reasonable price too. Again, standard piping components. Actually, I've got all the drawings for the seal molds, everything. So if somebody wants to pick up on this technology and start manufacturing, I have everything to support you and get you going. I no longer manufacture, but I'm acting as a consultant. And I'm quite happy to sell you a whole technology package that gets you into this business. It's a really nice business. And it can expand into something quite big, actually. So again, I'm available to do that. So that's one of the reasons why I'm putting this presentation together, to give you a nice understanding of how this technology works. All right, so let's go on. The U5 series, this is kind of the standard for most biggish applications. So the tubes, what kind of tubes can we use? Well, I say seamless. But I have seen in the early days that they even used welded tubes. And in fact, for low cost, you can use welded, almost like curtain rail. The trouble is, when you've got a welded tube, remember when you're welding, you end up with a heat affected zone either side of the weld, which actually changes the material. So if you're working with a stainless steel, you start to lock up some of the chrome in that, and you end up with chrome carbides and so on. And so the resistance of that tube is not the same as a seamless tube. Seamless is essentially the same properties all the way through, as long as there's no porosity. But with welded tubes, it can be problematic. And I had a case where colleagues who were building these units, they were putting them on the mines, and then they had failures. And I had a good look at it, and I remember I went up to the mine and sat with the engineer, and I said to him, tell me, how are you cleaning these things? Are you using CRP? They decided to use chemical cleaning. I said, have you changed the acid type that you're using? And he said, yes, we use. I said, yeah, there we go. So what was happening, that was actually going for this seam. And my advice to the builders is, don't use seamed, use seamless, and rather price around. And when I was there, I was actually able to get seamless tube for much the same price as welded tube. And for me, that's one less headache. It's a much better tube, and the chance of it lasting longer is better. You also don't have to go down to very, very thin. With some of these things, they were going down very, very thin because the elastomeric seals allowed it. They didn't damage the tubes. But I don't believe in that. I believe you need to have integrity. So you need a seamless tube for, at least a reasonable wall to give you some corrosion life. Okay. Components, I've showed you some of the components like pressure plates and so on, and you can actually make these to quite tight tolerances, especially using computer-aided manufacturing. And then the shell, essentially it's pressure grade process pipe. And I've done some work, developments of even higher pressure applications where in fact I use a much higher thickness of pipe and so on to actually get much higher pressures. Studs, high tensile material. Here be careful, people try and take shortcuts. They say, I can use stud bar, thread bar, I can cut it. No, you need high tensile studs really to get a proper job done and make sure you have the right material. So when I took over the business, I got all that side sorted out and took them back to what studs were meant to be in the first place. Coatings, yeah, you can actually coat with high temperature epoxies, typically outsides on that. In the internal surfaces, I would rather use seal backers rather than trying to use coatings, because the coatings are never perfect. And if you don't machine them back, it's a little bit tricky sometimes, for seals. But I mean, it works, but I don't always like it. And coatings can start to strip if you're not careful. And then seals, superior elastomeric quality. Again, you can, as long as your supplier knows what he's doing. The big thing is you must test your seals. I had cases where the guy who was making it sometimes put in too much hardener or too little, what do you call it, not softener, but basically, and they ended up being really hot. And so you would find that the sealing was a little bit of an issue. So you've got to really watch what your manufacturer is doing. So you have a bend test, and you have you put in what do you call it, an indenter test and so on. So you can actually make sure that the quality is right. It's very important. And then quality control, when you make these things, material certificates, very important. You must always keep your certs because that tells you if there's a problem, you can go back and see which batch went wrong. Welding and assembly procedures, well, there's no welding really other than to put this on the back, okay, to the shell. And then of course when you have these headers, if you're not a cast header, which you do get cast headers, but if you've got a welded construction header, which is the most common one for price, you really do have to look at your welding and assembly. Sometimes people don't, and the welding is very rough, and they still get away with it, but no, it can be better. And external inspection services, check the thing out, make sure it's right. And then Assembly 8 compliance. Essentially, it conformed with Assembly 8 because of the, ASME 8, should I say, because of the fact that the shell size was so small. Normally, there's a PV allowance, and we used to fall under the PV allowance, so we could actually comply. It was a trick. So depending on the country you're in, just have to check that out. Right? And then the idea of tank system, this is quite neat. You have two options. The one is you can have your tank, and then you actually put your bundle across the middle of the tank. So what's happening is the fluid is then coming across the bundle. So you have heating and cooling medium inside the tubes now across this bundle. You can use steam, hot water, hot oil, cooling water, whatever. I'd say moderate efficiency. They've used this quite a lot in hotels. Hotels and in hospitals actually in South Africa, where they had these bundles across. For me, I don't particularly like that method because what happens, the actual heating inside the tank then is difficult. You get the convection is not, it's not forced convection, it's natural convection, and it's hard to get the heat in actually to the water. The better alternatives always are an external heat exchanger. You can have it vertically mounted, or you can put it on the floor if you want to. Okay, an external pump, a little pump, and you pump around. The fluid is then circulated, through the heat exchanger, and then you can put the fouling fluid that might foul, depends what it is, inside the tubes, and they're pretty high efficiency. I like this idea for heating of tanks. It makes it very compact. You can mount them on the side, which is quite nice. They're not heavy. And then you have your little inline pump, and then you pump it in. But you really do have to always understand what's happening inside the tank. When you pump around, It's important because what happens is that the hot fluids rise, you see. So your hottest stuff's at the top. So if you're wanting to take your fluid out, you must make sure that you've got plug flow going up inside and everything's getting properly done. Most people say, just mix it all up. Well, no, it's not the most efficient actually to get your heat out. But if you want to be sure that you can pull from anywhere in the tank, well, that's okay, fine. Then you mix it up. Take a bit longer to heat, not the end of the earth. But that's something to think about when you do tank heating. But it's really nice. And this idea worked quite well. All right. And you can put steam in, so you can put steam on the shell side and take the condensate out the bottom, for instance. Sorry, on the shell side here, and you take the condensate out here. And again, you can also put in like a 3-way 90, and all of these are connected in parallel. We don't go more than 3. You could go to 4, but the trouble is then to get the right cross flow through the bundle. And if you notice, what's interesting is that you're on the shell side, you're going in here and taking out the opposite side. Don't put it here, because what you find is a graduation problem across these bundles. They don't all get the same flow. But if you put it this way, you do end up with better flow distribution on the shell side of the bundles. All right. The tube side, you'll find that they're squirting across, no problem. It's actually not as problematic, but still, I would always put it opposite, in and out. Okay. And then let's talk about some applications, U5 application. Let's talk about the single module, which I spoke about earlier on, where I said, okay, you've got the one with the socket straight onto the shell. Quite cheap, really. You save a header, and then socket on the inlet of the end cap. And then you've got the one with a double header, and then you get the vented seal arrangement over here. Okay, but still, these are slightly cheaper arrangements than construction-wise, single and vented. So this would be a single header, double header. And that picture you've seen before, but this picture kind of gives you an understanding of how this whole thing goes together, and I'll talk through this a little bit at the moment. What you've got is you've got your tube bundle here with your spiral baffles. Then you'll find that you've actually got, this is a pressure transferring, we're not showing you how it all fits together, right? And there's plates and so on in here, and then transferring pressure and seals. There's a lot going on inside here. This particular one here doesn't have a pressure transfer ring like you'd see here. It actually has we used pins on some of those to save money. These were quite expensive, these pressure transfer rings. So this was one way of doing it. And then we've got all seals involved here and at the end for the end cap and so on. And there's a seal that goes into this area here to seal your, we call it a ring seal. So there's a lot going on, and you've just got to understand what you're doing. But when you want to strip, it's very easy. You strip and you just start to take the pieces off. And then you can do the same on the other side, and then you slide the whole bundle back, have a look at it. If you're happy with it, that's cool. If it's basically all fouled up and so on, you want to give it a clean, you just blast it, give it a clean, put it back in, and then start reassembling. Make sure everything's nice and clean, you know. If you've got a leaking tube or you're not happy, you just take the tube out. You don't have to plug the tubes, put another tube in. And off you go. So it's really quite phenomenal, actually, as a technology. All right, it's a lot of fun. Now we start to get onto multiple modules, but now bigger. We've seen a small guy. We saw this little fellow here. But now when we start to get to big flow rates, when I spoke about designing, I spoke about the inside-out technique. So you start off as a designer and you say, all right, I've got a flow, and how many modules do I need to go in parallel? So what happens is there is a restriction on the velocity that we use. Too low, we've got a problem. Too high, also a problem. Wire drawing and erosion. Excuse me. So what we then do is we say, I can put 2 in parallel, or 3 in parallel, or even 4 in parallel. So this one's 4 in parallel, and so for that we typically put a 4-way manifold, and we then tie it up to the headers. If it's only 3 or 2, we can use these 2-way straights that I spoke about earlier on. Okay, it brings the cost down. These manifolds all cost a little bit. And you'll see sometimes for space, we actually even curve these manifolds so that they actually give us the space we need. We can get it all in. So this particular unit, if we look at the construction of it, we've got 1, 2, 3, 4, 5 in series. So it's 4 in parallel, 5 in series. So the parallel is determined by the amount of flow that you're trying to put through there, and the amount in series is really got to do with how much heat you're trying to extract out of the fluid. And at some point I'll do a study on and explain to you how it works in terms of things like we call temperature cross and all of that, and the heat recovery and how it affects the number of series passes you need. But this unit's quite long. It's probably 4 meters length here. And so if you've got 4 times 20, it's 20 meter long if you laid it out on the ground. So we wrap it this way and we use turnaround headers to get it all together. And each bank handles a certain amount of flow. And what we can do in some cases, let's say we say, well, my flow's dropped off, I don't need all that flow. You take the whole bank off, you just slice it off, and then you just blank off the manifolds. Okay. If you don't want to do anything silly, all you do is you pop the manifold back and you put a spacer in there. Okay. And with these, you can put spectacles or something so that you get the distancing right, and then you blank off a bank. You blank off 2 banks if you want to. It's very easy. It's so flexible. You can do all kinds of tricks with this construction. Again, I would like to work on that stand. I don't like these stands the way they've got them here. This one looks like wooden spaces. I think these are wooden spaces on this one. And this one here was an air aftercooler, if I remember rightly. And again, a lot of, this is probably sound damping and so on. But again, all these really interesting constructions. You've got parallel, and then you've got the series. And because of the space that they were involved in ins and outs of the plumbing, they had to put spaces in between so you could join up the different manifolds. And if you wanted to get bigger later, you could put more in parallel if you want, or get less, you can take some off. So it's very flexible. It's like a Meccano set. Very easy. This one again, all in parallel. If you look, there's spaces in here. Sometimes you could even put valves in if you want to, and you can valve off a flow. So it does. If you've got a process that needs to have adjustable flows, heat exchangers are designed for a fixed flow. So when you start to get flows that are variable, you start to run yourself into an efficiency problem, and then you start to get fouling, and it becomes a problem. If the flows are too low, you will foul that exchanger, drop out. It's just no question. If it's too high, you damage it. So what you could do in a case like this is you could say, I'll tell you what I'm going to do. I'm going to put some valves in here. And then what you do is you can automate those valves. Technology's advanced. And you can then switch in certain banks and switch out certain banks if you want to. If you wanted to get more complicated. And it'll actually give you a nice operating smooth plant. The heat exchanger is doing its job properly. Always, specially set up. These big exchangers are, the normal shell and tube type can't do it. They don't have this adjustability. We can do all of that with modular units. This is another unit, if I think rightly on this, it's 2 in parallel and then 5 in series. Okay? And then this little guy you've seen as well. So that you know all about. Okay. But again, very easy for a little workshopper. The stands, because they're not heavy. So the stands, with 2 stands here, you build it, and then when you finish, you give it a nice coat of paint and you're done. But the beauty is this could become something like that. Very simply, if a client has this and he says, no, I want to use this, but I want to go double my flow, we just stick another bank in parallel, and then we lace them together with two-way straight. So that means you'd have feeding from, I don't want to go too far back, but basically you can do it with essentially two headers laced together and an end piece coming in. You get up to 3. So you can then lace these together. So this could become a 9-module system without trying too hard at all. And if you wanted to put more in series, you can do that. So you can always readjust and re-rate units. Very simple. Very simple. And then going on to U5 applications, oil and gas. This was a special range that was done in stainless steel. Nice looking units. I personally would have preferred to see thicker studs here. I think these studs in my view just look too thin. They're fine once it pulls it up, but I would prefer to see thicker studs here, stronger studs. The manifolds are quite heavy duty. This was obviously quite a high pressure application as well. Also classic, you'll see the top in South Africa is always 2-hole top. I've seen some countries that I won't mention who they are, end up with 1-hole top. It's not a convention that we have. So this is stainless, and of course again you can pop this apart. It's not difficult if you know what you're doing. It's not difficult. This is the drawing that the designer would put together, and then the fabricator would literally just put it all together as a Meccano set. And if you've got a very good fabricator, a very good assembler with you, it becomes very easy for them. to do it. They just take the drawing and they can build it from there. You don't need much more complicated stuff. When you get towards petrochem and that, oh, they want a million drawings, but which is fine, doable, but it does cost. You don't always make the profit out of it because there's so much work involved. Okay, so these are crude oil heaters. So you'd use, in this case, probably steam, I'd imagine, and then your crude oil would be on the shell side. Let me check the sizing. Yeah. So this is probably probably steam. You could even use thermal oils in here, and then crude oil here on the shell side. And again, if you get a major blockage later, because crude oil is nasty stuff, you might have to pop it apart and give it a clean up. So you would just literally go here, pop the nuts and bolts off here and off there, and then just pull everything back, and then put it back together again. Very easy. You can do it in position. And then I won't go into detail here. I'll stop at this point. Next time we will talk about the applications in the gold mine industry, and this was really a fascinating challenge, because I remember my boss at the time came to me and he said, well, hey, we've got a lot of prospect up on the mines. Do you want to have a go at this project? So I said, all right. He said, but we just don't know the right size. In those days, what they wanted was an economizer, a heater, and then they were going to have a trim cooler here. And I said, let me go and have a look at it. So what did I do? I started off with a certain entry temperature, and then I said, okay, let me come out at a certain temperature, let's say unknown for now. Then goes into the heater. This is known, has to be 135 degrees out. That's cool. I've got a flow rate. So ultimately, he has to go from 25 to 135. Into the column is a bit of cooling, 130 out. It then comes back at 130. So these are fixed. Those are fixed. Then you come back 130, and then we're going to go to a cooler, and that was also fixed, the electrowinning. And so I started to build the study, and then what I would do is in steps. I'd go 25 to 30, and then 30 to 135. You had a big heater, small interchanger or economizer, and then I'd step it up by another 5 degrees, and I'd then step through, and then eventually say, no, well, hey, this is, and I got to a point that I realized, I don't even need a cooler, and this saved them a lot of money on the process. And so they accepted, eventually the client accepted excuse me, the technology, and it's been in the mines in South Africa for quite a long time. And the choice of heating, we could use hot oil or steam. Steam is actually quite efficient. Hot oil creates its own issues, thermal oils, because they can be very, again, it's not as good heat transfer as steam. Steam's marvelous. You could use low pressure steam, LP steam, don't even go to 10 bar, 6 bar steam, and comes in, and it ends up being quite a compact unit. And eventually what we found is the economizers were typically quite large and the heaters were quite small. I did see another manufacturer, friends of mine, who broke away from this original transheat, and they had a design that one of their friends had done for them, and he had a very large heater and very small economizers, and I realized, no, he hadn't done his homework. He hadn't gone to go and check what was going on properly. He hadn't optimized his final answer. It was ended up being a bit silly, really. So there are some rules that we established, and in South Africa, this was the typical way it's done. I see in Australia, people go for things like plates because they don't have these. The trouble is, under this application, the plates foul up. There's no question they foul up terribly because of the fact that it's sediment that's passing through it, all right, so what I'll do next time is I'll start off at this point for part 4 and talk through gold mining. And this is where, if people are in areas where you have gold mines, this is really a nice technology for gold mines. And I know it because it works well. And I used to remember seeing the units come back for maintenance and that, and the fouling was very small. I was actually surprised. I thought that it would foul a lot more than it did. Sometimes they fouled. If the miner's got a bit heavy on something, there's too much particle matter through, or they shut off their velocities, and eventually it starts to drop out. But generally, they were actually very accommodating. I was actually most surprised. Anyway, so I'm going to say let's call it quits for that, and then I'll walk through the rest later. All right. Thanks, everyone, for listening. Thank you. Bye-bye for now.